This content is produced by Darknet Breaker, a cybersecurity and dark web education brand. All videos, posts, and content are strictly for educational and awareness purposes only. We do not promote, support, or encourage any illegal activity. Our mission is to expose digital threats, protect online users, and educate the public about cybersecurity risks in the modern world. Stay ethical. Stay protected.
Traditional privacy networks, like Tor, are designed as synchronous, low-latency systems. They route interactive, real-time traffic to specific destination servers, protecting the connection line itself. But this model relies on the persistent availability of the destination host. If the destination server goes offline, goes black, or is seized, the connection fails entirely, and the data becomes instantly inaccessible. Furthermore, synchronous circuits require active, unbroken end-to-end communication. This makes them inherently vulnerable to timing correlation attacks by global adversaries tracking packets entering and exiting the network. Hyphanet, formerly known as Freenet, addresses this by functioning as an asynchronous, decentralized global cache with no fixed destination hosts. In this system, a publisher uploads files directly into the network structure. The publisher can then physically disconnect, and the data remains online, distributed across the hard drives of participating nodes. This architecture decouples data persistence from publisher uptime. Nodes blindly store encrypted chunks of data locally and use small world routing logic to forward requests toward the mathematical location of a file. This design prioritizes long-term data survival. It ensures that files remain available even if the original publisher is compromised or forced offline. Operating without a centralized directory or DNS creates an immediate engineering problem: how to reliably address and route both static files and updating websites across a blind peer-to-peer network. Hyphanet handles this using uniform resource identifiers parsed as cryptographic keys. Content hash keys, or CHKs, are the primary mechanism for immutable, static data. This slide breaks down the key structures. Looking directly at the content hash key section, the routing key is derived entirely by running the file's payload through a cryptographic hash. Because the address is the hash itself, it inherently guarantees data integrity. When a user uploads a large file, the protocol automatically chunks it into strict 32 kilobyte segments. It then supplements these chunks with forward error correction metadata, allowing the file to be reconstructed later if individual network blocks drop offline. Each CHK contains the SHA-256 hash used for network routing, alongside encryption settings and a symmetric decryption key. The protocol strictly separates the routing hash from the decryption key. Looking at the next block down, signed subspace keys handle mutable data. Here, the publisher generates an asymmetric key pair. They encrypt the file with a symmetric key and sign it with their private key, creating a namespace that anyone can read using the public key, but only the owner can write to. This asymmetric logic enables dynamic personal websites, known as free sites. The URI uses the hash of the public key as the routing identifier across the network, ensuring updates route correctly without requiring a static IP. Crucially, the symmetric decryption key is withheld from the individual storage nodes and is only passed client to client via the URI link. Node operators possess no keys to decrypt the specific chunks sitting on their own hard drives, achieving strict mathematical plausible deniability. That local storage mechanic requires rigid boundaries. Individual node operators configure a dedicated amount of hard drive space strictly to hold incoming encrypted 32 kilobyte chunks. As a node participates in the network, it blindly receives and stores these blocks. Because space is finite, the local data store quickly reaches its consequent capacity limit. To manage this, every Freenet node operates on a strict least recently used, or LRU, caching protocol. The data items in the stack are sorted continuously by the exact time they were most recently requested. When a new block arrives, it forces its way into the top of the stack. This physical displacement evicts the least recently used files at the very bottom of the list, permanently deleting them from that specific node. Unlike storage platforms that guarantee file lifetimes, Freenet has no permanent backend. The network possesses 0 centralized permanent copies of any file. Therefore, a file's lifespan is dictated entirely by network demand. Frequently requested data is refreshed and pulled back to the top of the stack, while unrequested data naturally ages out and is purged. By linking persistence directly to access velocity, the LRU mechanism continuously manages the finite global storage capacity through the autonomous, localized behavior of every independent participant. With files constantly shifting through independent data stores, the system faces a severe routing challenge, locating a specific segment across a massive peer-to-peer graph without querying every node.
This document details the routing logic. Hyphanet relies on the properties of navigable small world networks, where each node knows its physical neighbors alongside a few distant peers. It utilizes key-based routing, keeping the average path length between any two random nodes logarithmic rather than linear. To organize this, the protocol maps the entire network onto a one-dimensional circular coordinate space, bounded between 0 and 1. Every node is assigned virtual coordinates within this mathematical ring. Here, nodes build this topology dynamically. They continually send probe messages to negotiate location swaps with neighbors. A deterministic swap always decreases the average physical distance between key locations, while a probabilistic swap occurs randomly to break nodes out of localized clustering. This relies on the Metropolis-Hastings protocol. Tenectic nodes calculate the product of their current connection lengths and compare it to the hypothetical lengths if they were to trade virtual coordinates. If the hypothetical swap reduces the Manhattan distance between the nodes and their connections, the swap executes deterministically. If the distance increases, the swap executes probabilistically based on a strict transition formula to maintain overall network fluidity. Through continuous coordinate swapping, individual nodes gradually specialize in specific cryptographic data regions. This mathematical optimization transforms a highly unstructured peer-to-peer mesh into a rapidly navigable distributed hash table. Hyphanet operates across two distinct topological modes. The default configuration is Opennet, which relies on public seed nodes to bootstrap connections rapidly, integrating the user through automatic path folding. However, Opennet connects users automatically to unknown peers. This exposes the node's external IP address to strangers, leaving the participant vulnerable to active mapping and traffic analysis. The alternative is Darknet. This is a pure friend-to-friend configuration, where the node completely disables automatic peer discovery and exclusively routes traffic through manually verified trusted contacts. While Darknet relies on assumed real-world trust to prevent infiltration, the protocol reinforces this closed perimeter with robust packet obfuscation at the network layer. The client constructs a rigid transport envelope. The architecture fixes the maximum transmission unit at 1280 bytes, appending a 10-byte hash message authentication code, and padding the payload out with 0 to 64 bytes of random data. That strict multiple of 64-byte padding, combined with advanced encryption standard applied in periodic cipher feedback mode, strips away identifiable metadata. This neutralizes attacks where an adversary attempts to infer packet content based on varying traffic size. The two modes serve exact opposite priorities. Opennet accepts structural exposure to prioritize immediate scale, while Darknet leverages rigid cryptographic obfuscation and localized trust graphs to create an environment aggressively resistant to ISP-level traffic profiling. To see how addressing, storage, and topology interact, we have to trace a single data request. A client queries a CHK URI, initiating a probe message governed by a hops-to-live countdown to prevent infinite routing loops. The client forwards the request to the neighbor whose virtual coordinates are mathematically closest to the target key. This step-by-step routing continues until the network locates a node holding the correct 32-kilobyte encrypted chunk. Once located, the chunk does not jump directly back to the original client. Instead, it reverses course, routing backward along the exact identical chain of intermediary nodes that forwarded the original request. As the payload traverses this return path, it executes a critical function. The protocol forces every single intermediary node it touches to cache a copied instance of that specific encrypted chunk in its local LRU data store. This automatic replication mechanism pushes high-demand data outward from specialized nodes. The more frequently a file is requested, the wider it spreads across the active network, neutralizing single-point traffic bottlenecks. If a segment drops offline entirely, the client's forward error correction logic reconstructs the missing data. The system then automatically heals the network by reinserting the repaired chunk directly back into the cache stack. This architecture functions through a specific trade-off. Hyphanet sacrifices low-latency performance to ensure that every read and write operation cryptographically hardens the network's resistance to censorship.